Welcome to BITS 2020. My name is Jayakumar Radhakrishnan. I am one of the organizers of BITS 2020, along with Vivek Borkar, Nikhil Karamchandani, Vinod Prabhakar, and Bikash De, Shibiraj Pillai. Before I forget and we get too involved in our sessions, let us just thank the office staff, both at TIFR and at IIT, for putting everything together. So let's give them a hand. So this is the third edition of the seminar. The previous editions were in 2016 and 2018. Like the last edition, this edition is also being supported by Professor R. Narasimhan Endowment, which is an endowment at TIFR. This endowment was made by the family of Professor R. Narasimhan, who was the founder of the computer science activity at TIFR. In particular, he led the team that built India's first digital computer. There is information on Professor R. Narasimhan on the posters outside, and there is also an article in Current Science from early 2000s where he describes how things were at TIFR and in India when the first computers were being made. So Professor Narasimhan's contributions to computer science in TIFR, as you will see, were extraordinary and probably unparalleled. So this endowment, it has very many components. One of them is supporting an annual workshop like this. And as part of that workshop, we also have the R. Narasimhan Award Lecture. In addition to that, the endowment allows us to support a postdoc in the computer science department here, and some support for visitors to visit TIFR. This year, our Professor R. Narasimhan lecture will be given by Professor Rashmi Vinayak from CMU. Vinod, who will chair the first session, will introduce her formally. On behalf of the R. Narasimhan Committee, the School of Technology and Computer Science, and all of us here, let me just say a word of recognition. We are very proud of your achievements and your contributions to the field. And I'm sure all this will inspire the younger people who are in the audience. Thank you for accepting our invitation.
Thank you very much.
Yeah, Vinod.
Okay, so I didn't really plan to come up here. Rashmi is well known to all of us. So she received her master's degree from IISc, and many of our attendees are from IISc. And she has a PhD degree from Berkeley. Again, we have Berkeley representation too. And since then, she has been at CMU and has done a lot of very impactful work in the area of coding theory, distributed storage, and we'll hear more about that today, and also during the tutorial, which is on Friday, which I hope many of you will attend. So without further ado, since we're already running late, I'll invite Rashmi to give her award lecture.
Thank you very much for the kind introduction, Vinod and Jayakumar. Also, thanks a lot for this invitation. I would also like to personally thank Professor R. Narasimhan's family for giving this generous gift to TIFR, which has made this talk and also this entire workshop possible. Last night I was just reading through an article, autobiographical article written by Professor R. Narasimhan that Professor Jayakumar shared with me. It was very fascinating to learn about the history of the computing field in India when the computing field itself was being born. And in the beginning of the article, Professor Narasimhan also has written a very nice sentence where he says that his contributions were basically shaped by several people, projects, and ideas that he worked with. And this kind of sets a good tone for one additional acknowledgement that I would like to make today. I actually have my mother in the audience today, and it's very rare that she can attend any of my talks, so I would like to take this opportunity to thank her for everything. Okay, with that, moving on to convertible codes. This is a joint work with my PhD student at CMU, Francisco Maturana, and the work behind the motivation and the introduction for this work is a work in storage systems, which is a joint work with my PhD student Saurabh, who is co-advised with Greg Anger, who is a faculty at CMU. So the outline for the talk today is going to be as follows. I'll start with an introduction and motivation to this problem of what we are calling as code conversion. And then I'll present convertible codes, which is a framework to formally study this process of code conversion. And then I'll moving on to present lower bounds on a particular cost metric called the access cost for code conversion. Then present achievability results via explicit construction, which has high field size, and then present low field size explicit constructions and end with a summary. Okay, moving on to introduction. Large-scale cluster storage systems are the foundation of the data-driven systems that have enabled this data-driven revolution that we have seen in the past few years. And these storage systems typically are of large size and running into hundreds to thousands of disks, and even in some of the large-scale systems like cloud storage systems, it is literally millions of hard disks. And the amount of data stored can run into petabytes and even exabytes. And these systems are built incrementally over time as the demand grows. In such large-scale operations, failures are common. In fact, they are the norm rather than the exception. And disk failures are measured using a metric called annualized failure rate, which is basically the fraction of disks that fail in a particular year. When the storage systems were reasonably small, that is like about a decade or so ago, data replication was a common approach for adding redundancy to provide fault tolerance. That is basically having multiple copies of the data. But over time, as storage systems have become humongous, most large-scale storage systems today use erasure coding. Let us take a quick look at how erasure coding gets used in storage systems. So I'll take an example where we have an n equal to 14, k equal to 10 code, and I'm picking these specific parameters because these are the published parameters as used in Facebook's data centers. Since k is 10, when using such a code, you start with 10 data blocks and add 4 parity blocks because n is 14. And these 14 data blocks, which is 14 blocks of data, which is 10 data and 4 parity, are then stored on different hard disks, typically chosen from different failure domains, such as servers, racks, power domains, and so on. This set of 14 blocks, which correspond to one set of data units, is called a stripe, and I'll use this term stripe throughout the talk. Let's go into detail into the redundancy in storage systems. So the amount of redundancy that gets added into a storage system is a function of the parameters n and k of the erasure code used. Right? So in the example that we just saw, where n was 14 and k was 10, the amount of actual physical storage space used for a unit of logical data is 1.4x. And this redundancy comes with a significant cost because it requires additional hardware, and hence it requires increase in the dollar cost, literally the cost of the hardware, and in addition, increase in energy, cooling, physical space, and operations. And hence, it is crucial to add this redundancy in a resource-efficient manner. In my discussions with cluster storage operators at large companies, including Google, Microsoft, Facebook, and Amazon, even a single-digit reduction in percentage of the storage space is of significant value. Okay, so let's take a more closer look at how redundancy is configured in storage systems. So typically, the amount of redundancy is chosen in order to meet durability and availability requirements. And these two are measured using some metric. And a typical metric that is used for durability is mean time to data loss, which is basically modeling the storage system as a Markov chain and finding the mean time to data loss. And availability constraints are specified in terms of cost for reconstruction. That is, when some data block is unavailable, and if there is a read request to that data block, how much time does it take to reconstruct and serve that data? And then based on some average metric for the failure rate of the hard disk size, these parameters n and k for the erasure code gets chosen. So really, this choice of the redundancy configuration is made in a top-down fashion and not considering where the data actually gets stored, that is, on which disks and how they fail. So current redundancy configuration mechanisms really are agnostic to differences in the failure rates of different disk drives. We did a study on the disk drive failure data from production clusters at Backblaze, which is a data backup company, and we observed that failure rates vary significantly. They vary significantly across disk families. So on this left side, you see a plot where on the x-axis, there are different disk groups, which is basically different make and models. And on the y-axis is the AFR. I'll go into a little bit more detail on this data in a couple of slides. It is also well known that the AFR of hard disk drives varies significantly across time as the disk ages. So this is a textbook curve for AFR, which is called a bathtub curve because it looks like a bathtub. And initially, AFR is high, and it's called infancy period. And after some time, there is a low AFR period, which is pretty stable, and that's called useful life. And then after some time, AFR again rises, and that's called wear out or old age. Now, let's take a look at a bathtub curve from real-world data. So here are the disk drives, the make models in the backup company Backblaze's production cluster. And this data consists of disk failure data from 2013 to 2019. And there are roughly around 7 make models with significant amount of disks, more than 10,000, roughly around 10,000 disks. And here is a bathtub curve which is from this real world data, which looks very much like a bathtub curve that we just saw. Okay, there is infancy, useful life, and wear out. Okay, so now, under this implicit assumption of the current redundancy configuration schemes, disk drives fail similarly. And in this assumption, different stripes stored on different disks which have same amount of redundancy provide same amount of reliability. Right? However, as we just saw, real world is very different and disks fail differently. So in this scenario, two different stripes which have same parameters really have very different reliability. In fact, some of them which have same redundancy may have insufficient protection and hence risking data loss, and some other stripes might have wasteful amount of resources because they have more redundancy than necessary. And this raises the opportunity of actually tailoring the redundancy to the observed failure rates, especially during the useful life period where AFR is low and pretty stable. So in order to tune redundancy to observed failure rates, one needs to observe and track reliability data in action. So in a system, when there are multiple different disk groups, let's say X and Y, for example, they are deployed at different instances of time. They will enter useful life at different instances of time, and they will enter wear out at different instances of time. So let FT denote the fault tolerance scheme used, and FT default is the default fault tolerance schemes. So in order to tune the redundancy during useful life period, one would use the default approach during infancy and wear out, and tune the fault tolerance two specific values appropriate for that disk group's AFR during the useful life period. So in order to tune redundancy during the useful life period, then one needs to identify when to change such redundancy, what should that redundancy be, and also how should we change the redundancy. And this is what we looked at in our work on heterogeneity-aware redundancy tuner, which is an online redundancy tuner which actively engages with this bathtub curve observed in production and identify when to change and what values to change. It identifies redundancy schemes which will use the minimum amount of storage space to meet the reliability and availability requirements. So here is a plot of the storage space savings if one uses redundancy tuning on this data from production cluster at Backplace. And on the x-axis, again, these are these different disk groups, and on y-axis is the percentage storage space savings. And as we can see, this readily provides roughly between 11% to 16% of storage space savings, and this translates to significant amount of monetary savings running into millions of dollars right away. Okay, with this it looks like all storage systems should use redundancy tuning from today, right? However, redundancy tuning is not free. When AFR of a disk group changes, in order to tune the redundancy, we need to change the parameters of the erasure code, that is the rate of the erasure code that is employed on those disks. Right? So often, one needs to change both the length n and the dimension k of the erasure code employed. One might think that we can keep the dimension same and then just vary the length in order to change the rate. But often it is not sufficient because the restrictions from the availability requirements restrict the values of k that can be used. So often we need to change both k and n. Let's take a look at how one can convert an already erasure coded set of data into another erasure code. So the default approach would be to re-encode, right? So read all the data and compute the new parities. However, this is prohibitive in terms of the cost that it entails. So this is because typically a large number of disks transition their AFR at the same time. And this results in highly varying and large spikes of resource consumption in order to do this conversion. Here is a plot from the data from production clusters at Google if one would use conversion right away using the default approach on the failure data from Google's clusters. On the y-axis is the total I/O of the I/O bandwidth of the cluster that is used just for doing conversion, and on the x-axis is the date. As we can see, more than 100% of the cluster I/O bandwidth is consumed for several weeks if we use this default approach of conversion. So this is unacceptable cost for conversion. And thus, a key barrier to do redundancy adaptation in practice is converting already encoded data from one code to another code in a resource-efficient manner. With that, the first question that we should ask is it possible to beat the default approach at all? And as you might have guessed, the answer is yes. Right? That's why I'm giving this talk today. So let's take a very simple toy example. Suppose we want to go from one single parity check code to another, which is from dimension k to 2k. Right? So here are the two initial code words where the empty boxes are the data blocks and shaded blocks are the parity blocks. Now, in the final code word, the dimension is 2k, and I've kept the data blocks as is. Now, in order to generate the new parity block, we can just read only the existing parity blocks and XOR, and we will get the final parity block. Right? So this is significantly better than re-encoding, which would require reading 2k data blocks if we just do re-encoding in the naive way. Okay, so this is positive result in the sense that this shows that we need to study this process more formally. And this is what I will do in this next part, where I'll present a framework for studying this process of code conversion. So when doing this code conversion, we are basically converting data that is already encoded using an initial code CI, which is an NIKI code, into data that is encoded under a final code CF, which is an NFKF code. Both of these codes are over the same finite field, and they encode the same information in the initial and final configurations. The only difference is that they are encoded differently. The information encoded is the same. Now, in this framework to study code conversion, the first thing that we need to handle is the change in the value of this dimension, that is changing from Ki to Kf. Now, in order to make sure that we have the same set of information in the initial and the final configuration, we will consider LCM of Ki and Kf message symbols, and let small m denote this set of message symbols drawn from this finite field Fq. So conversion, when we have this LCM of Ki, Kf message symbols, really takes from multiple code words in the initial configuration to a different number of multiple code words in the final configuration. So this need to consider multiple code words, even to capture the simplest example of the problem, is different from other problems in coding theory looking at for storage codes. For example, if you've looked at local correction or regeneration codes, in both of these cases, considering a single code word is sufficient to capture the problem. But here, we need to consider multiple code words to capture the problem. Okay, so we are going from NI-KI code to an NF-KF code. And we will have, in the initial configuration, M over Ki code words, where again empty blocks are data blocks and shaded blocks are parity blocks. And going to, in the final configuration, which is at the bottom, we will have M over Kf code words. Now, since we have multiple code words, we need a way to specify which message symbols go to which code words. Right? So in the framework, we capture this by having an initial partition Pi, which specifies which message symbols map to which code words in the initial configuration, and similarly final partition Pf, which specifies how to map the message symbols into the final code words. So basically, both of these initial and final partitions tell us which message symbols from the initial code word maps to which message symbols in the final code word. So for example, one choice of Pi and Pf could map the message symbols from initial configuration to final configuration in this way. And in another choice, it could be very different. And this choice of these partitions makes a difference in the conversion cost. Okay, so coming back again, we are going from initial code Ci to final code Cf, and we have initial partition Pi and a final partition Pf. Another element that we need in the framework is the conversion procedure T, which takes as input a set of initial code words, where this notation Ci of ms represents the code word for message M encoded with the code C. So this conversion procedure T takes a set of initial code words as input and outputs a corresponding set of final code words. Let's take an example. So suppose we want to go from a 3-2 code to a 5-3 code. And here Ki is 2 and Kf is 3, so the LCM is 6, so we will consider 6 message symbols. One choice for initial partition could be this, in which the initial code Ci encodes AB, CD, and EF together. And one choice for the final partition could be this, where Cf encodes ABC and DEF together, since Kf is 3. Now, if we assume the codes to be systematic, which is a very good assumption to make for storage codes, since most, if not all, codes employed in real-world storage systems are systematic, then the conversion would look something like this. We go from 3 code words encoded under the initial code to 2 code words, 2 final code words encoded under the final code. Okay, so now putting all these ingredients together, NIKI, NFKF convertible code consists of 3 elements. 1, a pair of codes CI and CF defined over finite field FQ. A pair of partitions PI and PF, which basically map message symbols to initial and final code words respectively. And a conversion procedure, which takes set of initial code words encoded under the initial code CI and converts it into a set of final code words encoded under the final code CF. Now, the cost of conversion is basically the cost of the conversion procedure T. And our goal would be to design so as to minimize this cost of conversion. And there are 3 degrees of freedom for our design. One is designing the codes CI and CF, designing the partitions PI and PF, and designing the conversion procedure T. And this would be for a given set of parameters Ni, Ki, and NFKF, subject to desired decodability constraints on both initial code and the final code, because both of these codes encode data in a storage system at some snapshot. So we need to satisfy the decodability constraints. One example for a typical decodability constraint is the maximum distance separable, or MDS property, which just means that if we have encoding with an NK code, any k out of the n blocks should be sufficient to decode the data. And there are various metrics to optimize for. So there is access, which is basically the number of disks touched during the conversion process. There is network bandwidth, that is the amount of data transferred across the network. There is disk I/O bandwidth, which is basically the amount of data read and written from the disks. And then there is CPU, or the computation cost. In this talk, I'll address one portion of this design space, basically focusing on the scenario where both the initial and the final codes are linear and MDS. Linear assumption is a very good assumption again for storage system codes, because again, all, if not all, as far as I know, all of the storage systems use linear codes. And a majority of the codes used in storage systems again are MDS. And also, linear and MDS is a good starting point to explore convertible codes. And in this talk, in detail, I'll cover one specific parameter regime, which we call the merge regime, which basically takes multiple set of initial code words and merges them into one final code word. So basically, we have Kf is lambda times Ki, where lambda is an integer greater than or equal to 2. So lambda represents the number of initial code words merged together into one final code word. And Ni and Nf can be arbitrary values. So on the right, you can see the merge regime would look something like this. You start with lambda initial code words and then merge it into one final code word. So this merge regime plays an important role, and in building up into covering all the general parameter regimes, but however, I'll not have time to cover it today. Okay, so we will be looking at linear plus MDS and merge regime in detail. And for the cost metric, I'll be focusing on the access cost, which is the number of code symbols affected during conversion. So each symbol that is read from the initial code words will cost an access, and each symbol that is written in the final code word will cost an access. So the access cost is number of symbols read from the initial code words plus number of symbols written in the final code word. Okay, so with this, let's move on to lower bounds on the access cost for code conversion. Let Ri be Ni minus Ki, and similarly Rf be Nf minus Kf. An intuitive way to remember R parameter is to think of systematic codes. So if the code is systematic, then n minus k refers to number of parities. So Ri would be number of parities in the initial code, and Rf would be number of parities in the final code. So the results that I'm going to present today are not restricted to systematic codes. It is applicable in general, but this would be a very intuitive way to understand the results. Okay, so the theorem is here. So for all linear MDS convertible codes in the merge regime, in this case when Rf is less than or equal to Ri and Ki, the access cost is as shown. So here, the first term corresponds to the read cost, that is the number of symbols read from the initial code words. So it turns out that this is lambda times Rf. Basically, you're reading Rf symbols from each of the lambda initial code words. And Rf is the write cost, which is the number of new symbols written in the final code word. And if you recall, the access cost is sum of number of symbols read and the number of symbols written. And if this condition is not satisfied, then the access cost is greater than or equal to the value shown here, which again has two parts. One is the read cost, and in this scenario, we're reading Ki symbols from each of the lambda code words in the initial code words, and Rf is the number of symbols written, which is the write cost. So basically, it is in this first scenario that we can do better than the default approach, right? So that is when Rf is less than or equal to Ri and Ki. And in the second scenario, this cost is same as the default approach if we are reading Ki from all the initial code words and then writing Rf new symbols. Okay, so now I'll present the proof sketch very quickly. So I'll introduce two notation. So we will call unchanged symbols as those symbols which remain as is in the final code word as they were in the initial code words. Okay, so these symbols, if you're not reading it, then they are untouched. They'll remain as is and they need not be moved, so they won't cost in terms of access. And new symbols are the symbols that are new in the final code word. So they were not present in the initial code word, so they need to be generated and they need to be written. So the proof involves 4 key steps, and I'll quickly walk through them. So the first step is on the equivalence of the partitions. In the merge regime, specifically only in the merge regime, all possible pairs of partitions Pi and Pf are equivalent up to relabeling. However, I do want to note that partitions become very important when we go to the general parameter regime, and the cost is a function of the partitions. But for the merge regime, we can neglect partitions, and we don't need to specify them. And the second step is an upper bound on the maximum number of unchanged symbols that can be there. So in any linear MDS convertible code in the merge regime, there can be at most Ki unchanged symbols from each of the initial code words. This essentially follows from the MDS property. So we cannot have more than Ki symbols unchanged from any of the initial code words. So we will call convertible codes as stable if they have exactly lambda Ki unchanged symbols. That is, stable convertible codes will have exactly Rf new symbols. So if you recall, R was n minus k, right? And Kf was lambda times Ki, which is what we have as the number of unchanged symbols. So the only number of symbols left is Rf. So those are the new symbols. The third step is a lower bound on the access cost for stable convertible codes. So we will now first restrict our attention to stable convertible codes. So recall that in the previous slide we just saw that stable codes exactly have Rf number of new symbols. Also recall that access cost was sum of symbols read and sum of symbols written, and sum of symbol written is basically new symbols, which is Rf, which is fixed. So the only thing that we need to specify now is the number of symbols read. And here, for any linear MDS stable convertible codes, remember that we are now restricting to stable codes, one must read at least minimum of Ki and Rf symbols from each of the initial code words. And also, if RF is greater than RI, then one has to read KI symbols from each of the initial code word. Now, if you look at the cost in the first case, we have min over KI and RF. And recall that for the default approach, we need to read KI from each of the code words. So in order to do better than the default, we need RF to be less than KI. This was one of the conditions in the theorem where we can do better than the default approach. And also here, if you see, again, reading KI from each of the initial code words means same as default approach. And hence, in order to do better than default, we'll also need RF to be smaller than or equal to RI. Okay, this corresponds to the two conditions that we had on RF in order to be able to do better than the default approach. Now, the fourth step is to remove the stability constraint. So the lower bound that we had in step 3 was only for stable convertible codes. Now, we remove this stability restriction by showing that convertible codes that are not stable necessarily require higher access cost. That is, basically all access optimal linear MDS convertible codes in the merge regime are stable. So it is okay and it suffices to consider only stable convertible codes. And hence, the lower bound that we saw in step 3 applies to all convertible codes, not just stable codes. And this gives us this result that we saw earlier. It turns out this lower bound is achievable, and that's what I'll move on to next. So I'll present achievability through an explicit construction, and this explicit construction applies for all parameter regimes applies to all parameters in the merge regime, and it is also systematic. So the first case where RF is greater than RI, or when it is greater than or equal to KI, is trivial because, as we saw, the cost is same, the lower bound is same as what the default approach can achieve. So there is nothing for us to do there. So the interesting case is case 2, where RF is less than or equal to min of RI and KI. So for this case, and as I mentioned, since the construction is systematic, let the generator matrix for the initial code CI be GI, and since it is systematic and MDS, it will be of this form IP. And similarly, for the final code, let the generator matrix be GF, it's the same form I and P. So first, I'll talk about some structural properties that these matrices need to satisfy in order to be access optimal convertible codes, and then present a construction and then show that it satisfies those properties, and then we will be done. So the first property is a well-known result on MDS codes, which is basically saying that for an NK MDS code with generator matrix I and P, matrix P needs to be superregular. That is, basically any submatrix of P needs to be non-singular or full rank. So in order to be MDS, we need both PI and PF, which is basically the part of the generator matrix corresponding to parities, to be superregular. Okay, this is property 1. Now the property 2 corresponds to the conversion process. So we are calling this property as T-column block constructible. So first, let's see a simpler property, which is T-column constructible. So we will call a matrix M1 to be T-column constructible from another matrix M2 if and only if there exists a subset of size T of columns of M2 that span the columns of M1. That is, basically, we can generate columns of M1 using some subset of the columns of M2 of size T, and T is the parameter. Now, using this, we'll build up to block constructible property. So we will call T-column block constructible. So we will call a matrix M1 now, which is of dimension lambda n times M1. So it's a tall matrix. Is T-column block constructible from this matrix M2 if some property holds. And before moving on to that property, I want to remind that now M1 is a tall matrix and M2 is a short matrix. And the property is the following. So it's if and only if every submatrix of M1, which is of height of matrix M2, and it's a row-wise block submatrix. So if those submatrices is T column constructible from M2, which we saw earlier. So basically, M2 needs to span each of these submatrices. Now let's see how this relates to the code conversion process. So recall that for access optimal linear MDBS codes in this regime that we are talking about, the read cost was RF from each of the initial code words, right? So the read cost was lambda times RF. So it suffices if we have the matrix PF such that it is RF column block constructible from PI. What this basically means is that you can read RF symbols from each of the initial code words and then generate the new parities in the final code word. Okay, so putting these two properties together, a systematic convertible code in the merge regime is MDS and access optimal if the following two properties hold. One is super regularity, and PF is RF column block constructible from PI. Okay, so now let's see a construction and something that satisfies these two properties. So consider a field of size 2 to the d, and d will be made very large very soon. And let theta be the primitive element of this field. And G, I, and Gf are the generator matrices, as we saw earlier already. Now the matrices, the parity part of these generator matrices, Pi and Pf, take this form, which basically has the form where each ijth element is theta to the power I minus 1, j minus 1. Both Pi and Pf have the same structure. So let's take an example. So suppose we want to move from a 6.3 code to a 9.6 code. So in this conversion, both initial and the final configurations have the same R, which is 3. Okay? So Pi is going to look like this, and Pf is going to look like this. So the conversion process really looks as shown on the right, where again empty boxes are the data blocks and the shaded boxes are the parity blocks. So the data blocks remain as is, and they are not touched when we convert from initial to final code. And the new parities for the final configuration are generated using the existing parities in the two initial code words with a specific linear combination using powers of theta. So this construction yields access optimal MDS convertible codes for all parameters in the merge regime. And essentially what we have to show is that it satisfies those two structural properties that I established earlier, right? So by design, here Pf is RF column block constructible from Pi. So you can go back and look that we can actually stack Pi vertically with some carefully designed powers of theta to get Pf. And also, Pi and Pf can be made super regular for sufficiently large field size. So it satisfies both the structural properties. One caveat here, however, is that it is for sufficiently large field size, and the field size is really large. So it's not a practical construction. So now next, I'll move on to low field size explicit constructions. So the key idea here in low field size constructions is to draw the matrices Pi and Pf, which are the parity part of the generator matrices, from a specially constructed triangular array which takes this form. Here BIs are not necessarily distinct. They can be same. So observe that this matrix has this structure where if you look at left hand bottom corner to right top corner, along the diagonal, the elements are identical. This form is called a Hankel form, and such an array is called an Hankel array. So let's take an example to see how we use Hankel arrays to construct these codes. So suppose we want to convert from an n equal to 9, k equal to 5 code to an n equal to 12, k equal to 10 code. So here in the initial configuration, R is 4, and in the final configuration, R is 2. For this example, we will use a Hankel array of size nf minus 1, which is 11. So here is the Hankel array of size 11. And we choose this parity part of the generator matrix Pi and Pf as shown here. So since Ri is 4, Pi has 4 columns. And the first 2 columns are taken from the first half and the first 2 columns of this array. And the other 2 columns are taken from a different location of the array. And Pf, since R is 2 in the final configuration, Pf has 2 columns, and those 2 are the first 2 columns of this Hankel array. Now first, we can see that Pf is 2-column constructible, block constructible from Pi, right? Because the first half is identical to the first 2 columns of Pi, and the last half of Pf, that is the bottom half, is identical to the last 2 columns of Pi. So it satisfies this block column constructible property. And the field size here is nf minus 1 and 11, which is 11 here. Okay, so it satisfies one of the 2 properties, right? So recall that we needed 2 properties, and the other property was superregularity. So the first property, as we saw, is guaranteed by design. Now for this second property, the superregularity property, we will impose an additional constraint to make every submatrix in this array to be superregular. It turns out there exist algorithms to construct such superregular Hankel arrays. And these were designed in the context of designing generator matrices for specific type of MDS codes. So the construction based on these Hankel arrays yields a sequence of constructions which we are parametrizing using this parameter S. And this leads to a trade-off between the field size and the parameter range, specifically on the value of RF that you can cover. So the more the parameter range we can cover, the field size increases. But the field size is still very practical and manageable. It's not as large as the achievability construction. Okay, that covers the merge regime. As I was mentioning, for general parameter regimes, merge regime plays an important role. But another important regime that is needed to cover this general parameter regime is what we call split regime. And split regime is exactly opposite to the merge regime. That is, we go from a single initial code word into multiple final code words. So now ki is lambda times kf. So you're splitting one initial code word into lambda final code words. So we use this merge regime and the split regime and some slight generalizations of this to cover all the parameter regimes. Okay, in summary, heterogeneity-aware redundancy tuning in storage systems has a significant potential for saving storage space and ensuing reduction in the dollar cost for hardware, energy, cooling, and so on. However, a key challenge for practical adoption of redundancy tuning is resource-efficient conversion of already encoded data from one code to another. So I presented convertible codes, a framework to study code conversion, and talked about tight lower bounds on the access cost for conversion for linear MDS convertible codes. I also talked about matching explicit constructions for all parameters, which however had high field size, and then presented low field size explicit constructions. With that, I'll end my talk. Thank you, and I'll be very happy to take any questions.
We have mics. We should have mics around, so please raise your hand if you have questions. I'll also invite Rajesh to set up for the next talk. Okay, Rajesh has a question. Okay, so let's.
So one thing that was not clear is the construction dependent on the rate of the final code? If, for example, I find that the setting is such that I need to change the parameters of the final code given the circumstances, is it adaptive?
Right. Very good question. Actually, I didn't have time to cover it, so thanks for asking this question. So here I presented the setting where we need to know NIKI and NFKF, and it's a very good question that often we might not know it, right? It turns out that the constructions turn out to be adaptive. That is, the codes designed for a specific value of NF and KF are also optimal for several parameter regimes for the final code. And we have some excuse me, so details in the paper, the ITCS paper, which I didn't get time to cover it. But it would be certainly interesting to explicitly capture that in the framework as well. So currently in the framework, we have fixed for given NFKF, but it turned out, luckily, that the constructions actually are optimal for several parameter regimes. Very good question, thank you. Any other questions?
So let's thank Rashmi again.
Thank you all.
And just to remind you again, she'll be giving a tutorial on distributed storage on the last day of the workshop.
Yeah, and also on coded computation, 2 parts.
Coded computation, that's right. So that'll be on Friday.